Imagine you're a pilot, not just flying an aircraft, but really commanding an entire digital armada.
Mm.
You're facing just this absolute tsunami of information, making split-second decisions, lives and missions on the line.
Yeah, intense pressure.
Exactly. Now, what if right there in that cockpit, you had an intelligent assistant, a true co-pilot,
Oh.
something that's not just filtering the noise, but is literally helping you think clearer, faster, more effectively.
Interesting.
Today, we're embarking on a deep dive into that very future. The fascinating world of the AI-powered cognitive co-pilot for next-generation aviation.
And our mission for you, our listener, is really to cut through the complexity. We're looking at research papers, technical guides,
Right.
describing this revolutionary technology.
Yeah.
And our goal is pretty much to pull out the most important nuggets of knowledge, the key insights for you.
Helping people understand not just what it is.
Exactly. But why it matters so much, why it's so profound for the future of, well, human-machine collaboration.
Okay, so at its core, this AI, it aims to solve a critical problem, almost paralyzing. Cognitive overload.
Yeah, that's the term.
Think about it. Modern aviation, it involves this immense torrent of inputs, right?
Yeah.
Countless sensors, plus this increasingly complex job of orchestrating crewed and uncrewed assets. All this data can lead to something called cognitive tunneling.
Right.
Like imagine trying to find a specific key in a huge, messy junk drawer. You're so focused on one little corner, you completely miss the key right there in front of you.
That's a good analogy. Yeah.
That's cognitive tunneling. The pilot fixates on one data point, misses the bigger picture,
Yeah.
and that really impairs decision-making.
It can be dangerous.
Totally. So the real genius of this co-pilot isn't just, filtering data. It's about reclaiming cognitive bandwidth for the human pilot.
Reclaiming bandwidth. I like that.
Yeah, letting them operate at peak performance when every second counts. It's a fundamental shift, really, from human managing information to human mastering the situation.
That's a key distinction.
So we've outlined this critical problem, cognitive overload. But I'm curious, what are the specific shifts happening, in this next generation of aviation that make this AI not just helpful, but absolutely indispensable? What's really different?
That's a great question because, yeah, the environment itself is changing fast. One of the biggest shifts, like you said, is that overwhelming flood of data.
The data deluge.
Precisely.
Yeah.
Pilots are truly inundated. Information from their own aircraft sensors, from autonomous wingmen, satellites, ground systems. It's coming from everywhere.
Wow.
And this creates a serious risk of that cognitive tunneling we talked about. Critical information might get missed simply because there's too much to process.
So the need is filtering.
It's more than filtering. It's distilling, prioritizing, and presenting it effectively. So it actually enhances situational awareness rather than, accidentally diminishing it.
Okay, that makes sense. And then we have this other thing you mentioned, the dawn of crewed-uncrewed teaming, or CUT.
CUT, yeah.
So we're talking a future where one pilot isn't just flying their plane, but commanding a whole formation, leading a team of autonomous, loyal wingmen.
Exactly. That's the vision.
That sounds incredibly complex. What new challenges does that bring?
Though it adds entirely new layers of complexity.
Yeah.
You're not just managing your own aircraft anymore.
Right.
You're also managing the autonomy of these uncrewed assets. You're assigning them tasks, maintaining overall team awareness.
Yeah.
All in real time, in dynamic situations. And this dynamic environment also means that, well, traditional training methods, the one-size-fits-all approach, just isn't enough for these kinds of scenarios.
So that's the third challenge.
That's our third challenge.
Good.
The need for adaptive and personalized training. We need systems that can tailor training, maybe even in real time, adjusting based on a pilot's performance, maybe even their cognitive state,
Okay.
making it highly specific, highly efficient.
That adaptive part is really interesting, which brings us to, well, maybe the elephant in the room, this idea of a trust barrier. If an AI is going to be a true co-pilot, in a life or death situation, how do you even begin to build that deep, implicit trust? How do you make sure it's not just some black box spitting out commands?
That is the ultimate hurdle.
Yeah.
And it's absolutely non-negotiable. For pilots to truly collaborate with AI, they must implicitly trust the system.
Has to be there.
Yeah. And this means the AI can't just be accurate. It also has to be explainable. It needs to articulate its reasoning.
So it can say why it's recommending something.
Exactly. This isn't just about building trust, though that's huge. It's about transforming the AI from, like you said, a black box that just gives answers
Right.
into a transparent collaborator, one that explains its reasoning, empowering the pilot to actually understand, to validate, and then confidently act on its insights, just like they would with a human co-pilot.
Okay, so that makes sense. So how does it actually do all this? What's in the AI toolkit?
Well, to address all these challenges, the Cognitive Copilot leverages a suite of powerful AI technologies.
Yeah.
First, there's cognitive AI. This often uses principles from a field called neuroergonomics.
Neuroergonomics.
Yeah, it focuses on understanding and augmenting human cognitive performance. And it uses biometric sensors to non-invasively monitor a pilot's real-time cognitive state.
Got it. What else?
Then we have reinforcement learning, or RL. This is a really powerful way to train AI agents to make optimal decisions in complex dynamic environments.
So that's for the uncrewed stuff, the wingmen.
Exactly.
Yeah.
It's ideal for developing the autonomous capabilities of those uncrewed assets in the CUT scenarios.
Okay.
And as we just talked about, there's explainable AI, XAI.
The transparency piece.
Right. These are the techniques that let us sort of peel back the layers of complex AI models. They provide real-time explanations for the AI's recommendations to build that crucial trust and make the human-machine collaboration actually work.
Makes sense.
And finally, there's a foundational technology kind of connecting all of this. Digital twins.
Ah, digital twins. Heard a lot about those.
Yeah, they're high-fidelity, real-time virtual replicas of physical assets, like the aircraft, the sensors, the environments.
Okay.
And they serve as a primary platform for safely and, importantly, cost-effectively training and validating these AI models before they ever get near a real aircraft.
That's a fascinating toolkit. Let's dig into that cognitive AI piece a bit more. How does the system actually know what's going on inside a pilot's head? How's it monitoring their cognitive state without being, intrusive?
Right, good question. That's where the multimodal cognitive state assessment model comes in. It's basically a sophisticated deep learning model.
Multimodal, meaning multiple inputs.
Exactly. Imagine like a medical-grade cognitive dashboard for the pilot, but it's built on subtle, non-invasive signals. It integrates time series data from various biometric sensors, gives a really comprehensive picture.
Like what kind of sensors?
Well, for instance, EEG, that's electroencephalogram, it picks up brainwave activity.
Brainwaves, okay.
Yeah, looking at how quickly and strongly different brainwaves are firing. Alpha, beta, theta bands. These correlate to different states of alertness, focus.
Interesting.
Then there's FNIRS, functional near-infrared spectroscopy.
FNIRS, okay.
That gives us a clearer picture of blood flow in specific brain areas, especially the prefrontal cortex, which is tied to executive function decision-making.
So where the thinking happens.
Pretty much. And of course, eye tracking. That reveals where a pilot's focus is, how long they fixate on things. Even pupil changes can indicate mental effort.
Full dilation,
Yeah,
right.
right. And finally, ECG, electrocardiogram. That gives us vital heart rate data and heart rate variability. Tells us about their overall physiological arousal, stress levels.
Wow, okay. So you combine all that.
Exactly. This fused data is processed through that deep learning architecture, and it classifies the pilot's cognitive state into practical categories. Things like underloaded board, optimal, high workload, or even overloaded saturated.
And the co-pilot uses that information.
Yes, allows the co-pilot to respond appropriately, maybe simplify the display, suggest offloading a task, or even adjust the training scenario if it's in a sim.
That's incredibly sophisticated. So the AI literally has a sense of the pilot's mental state. Now, what about those loyal wingmen again? How does the AI manage a team of autonomous robots? And critically, how do pilots learn to trust an AI that's controlling their robotic teammates?
Yeah, that's where things get really interesting with the AI training. What's fascinating here is the hierarchical multi-agent reinforcement learning, or HMARL, approach.
HMARL.
This is the core method for training the AI that manages the uncrewed assets. And crucially, it happens exclusively within that digital twin environment.
All in the simulation.
All in the sim, allowing for just massive amounts of scenario training. This isn't just, basic simulated training. It's a revolutionary approach. Continuous risk-free iteration. The AI essentially gets lifetimes of flying experience before ever leaving the lab.
Wow. A lifetime.
Yeah, and the system uses something called centralized training with decentralized execution, or CTDE.
CTDE, what does that mean?
It means that during the initial training phase, there's a sort of central critic, an overarching intelligence that guides all the agents, all the wingmen, to learn optimal team behaviors.
Okay, so they learn together.
Right. But then, in a real-world scenario, during execution, each uncrewed asset makes decisions based only on its own local observations.
Ah, so they don't need perfect constant communication.
Exactly. It ensures robust performance even when communication isn't perfect or maybe gets jammed. Decentralized execution.
Smart.
Another key technique is reward shaping.
Reward shaping, like training a dog.
Sort of, but much more complex. It's not just about good or bad outcomes overall. It incentivizes specific things, both individual actions, like, say, maintaining formation,
Okay.
and cooperative team objectives, like neutralizing threats together. And critically, it penalizes undesirable outcomes, things like collisions or getting detected by the enemy.
Right, you need penalties too.
Absolutely. And coming back to trust, the explainable AI module is integrated right into this MRL system.
So the explanations are built in.
Built-in. This
Yeah.
module literally shows the pilot the AI's thought process in real time.
How does it do that? Like, what does the pilot see?
Well, it might use something like a surrogate model. Think of it as a simpler, more talkative version of the complex AI.
Okay.
It can clearly explain the rule-based logic it's using. Or another technique is using attention mechanisms.
Attention mechanisms.
Yeah, imagine like a heat map overlaid on the pilot's display. It shows exactly what pieces of information, which sensor readings, which targets the AI was focusing on when it made a particular recommendation.
Ah, I see. So you can see what it was looking at.
Precisely.
Yeah.
And the goal is to translate all that technical reasoning into clear, concise, natural language, stuff that makes perfect sense to the pilot in the heat of the moment, building that essential transparency and confidence.
Okay, that makes the trust part seem much more achievable. So, the digital twin. It keeps coming up. It's obviously way more than just a place to train the AI. What's its full impact here? Beyond just being like a virtual sandbox.
Yeah, it really is fundamental. If we connect this to the bigger picture, the digital twin plays two absolutely critical roles.
Two roles. Okay.
First, as we've touched on, training and validation. It acts as this super high-fidelity simulation of the aircraft. It sensors the entire operational environment, the weather, the threats.
Well, whole 9 yards?
Pretty much.
Yeah.
And this allows that multi-agent reinforcement learning agent, the one controlling the wingman, to be trained for literally millions of hours.
In millions. Wow.
Millions. And the entire cognitive co-pilot system, including the human cognitive state monitoring, can be validated safely, cost-effectively, and scalably before any physical deployment. It's a risk-free testing ground that just accelerates development exponentially.
Reduces real-world flight testing needs too, I imagine.
Massively. And its second critical role is for adaptive training for the human pilot.
Ah, right. We mentioned that earlier.
Exactly. The digital twin is used to generate dynamic and adaptive training scenarios for the pilot themselves.
Driven by their cognitive state.
Directly driven by the real-time assessment of their cognitive state from those biometric sensors. So, the training becomes incredibly personalized and effective. It can target specific areas where the pilot needs to improve, or maybe ease off if they're showing signs of overload.
That's really next-level training.
It really is.
Okay, so we've built this incredibly intelligent system, trained it for millions of hours in this amazing virtual world. What are the major hurdles then to get it from the lab into an actual aircraft, especially when it's, a mission-critical AI operating in such a dynamic environment?
Yeah, deployment is a whole other challenge. It requires an extremely robust MLOps pipeline machine learning operations with very specific considerations for safety and reliability.
MLOps for aerospace. Okay.
Right. First, you need continuous training and validation in the digital twin. Any new real-world flight data, any unforeseen scenarios encountered, they must be used to continuously update that digital twin.
Keep the twin current.
Exactly. And the AI models then need to be continuously retrained and revalidated against benchmark scenarios within that updated twin. It's a constant cycle.
Okay. What else?
Then there's rigorous model versioning and traceability. Yeah. You need meticulous tracking of every single model version, the data it was trained on, its validation performance.
It's like a pedigree for the AI?
Precisely. It's essential for safety certification and for forensic analysis if anything ever goes wrong. Also, edge deployment is key.
Meaning getting it onto the plane itself?
Right. These trained models, which can be huge, must be optimized for deployment on the aircraft's limited edge computing hardware.
Right. Not cloud-based.
Definitely not. So this involves techniques like model quantization, pruning, basically making the model smaller and faster without losing too much accuracy.
Okay.
But honestly, the most crucial final step is human-in-the-loop validation.
Pilots testing it out.
Extensively. Any new AI version has to be thoroughly tested by human pilots in those high-fidelity simulators before it's cleared for actual deployment in a real aircraft. It's the ultimate safety check.
Makes sense. But what happens, say, if the human disagrees with the AI's recommendation during one of those tests, or even in real life? How does the system handle those moments of divergence, especially if the AI is, like, certain about its conclusion?
That's a fascinating challenge, isn't it? The human-AI partnership dynamics. Generally, the design philosophy is human on the loop or human in command.
Meaning the human has final say.
Ultimately, yes.
Yeah.
The AI advises, explains, maybe even warns, but the pilot retains authority. However, the system might log these disagreements to refine future training or identify potential flaws in the AI's reasoning or the human's understanding. It's a learning process for both.
Okay, that's reassuring. So, stepping back then, what does this all mean beyond the cockpit? This whole AI concept, the cognitive co-pilot,
Wow.
seems incredibly powerful. Where else could you see this kind of thing making a fundamental difference outside of aviation?
Yeah, that's an important question. Because if you generalize the core concept right, an AI assistant that monitors human cognitive state, provides explainable decision support, maybe manages complex autonomous systems.
That core idea.
That core idea, yeah. The applications are truly wide-ranging. Imagine a surgical co-pilot.
In the operating room.
Exactly. Monitoring a surgeon's cognitive state during long, complex operations, providing real-time feedback, maybe highlighting tissue anomalies the surgeon missed due to fatigue, or even guiding robotic surgical instruments more steadily.
Wow. Reducing fatigue and error.
Potentially, yeah. Or think about an industrial plant co-pilot, assisting human operators in managing complex processes, chemical plants, power grids,
High-stress environments.
very high stress, optimizing efficiency, preventing accidents by maybe anticipating human error based on cognitive load, or predicting system failures.
Okay, I can see that. What else?
You could even have an autonomous fleet co-pilot, helping a single human operator manage a whole fleet of autonomous vehicles.
Like delivery trucks or drones.
Yeah, exactly. Providing high-level command and control, optimizing routes for the whole fleet, handling exceptions or complex situations that the individual autonomous systems can't manage on their own.
One person managing dozens or hundreds of vehicles.
That's the potential. Even in, say, the financial world,
Yeah.
a financial trading co-pilot.
Really? How would that work?
Well, it could potentially monitor a trader's cognitive biases. Are they showing signs of overconfidence after a win or excessive risk aversion after a loss?
So monitor the trader's psychology.
Coupled with providing explainable market analysis and risk assessment, helping them make maybe more rational, informed decisions under intense market pressure.
That's quite a range of applications.
It really is. And ultimately, what this all represents is, I think, a profound paradigm shift.
How so?
Well, it's not about replacing the human. That's the key thing. It's about truly augmenting their capabilities.
Human plus AI.
Exactly. Allowing performance levels that would likely be impossible for either the human or the AI working alone. It's about achieving a kind of human-machine symbiosis that could unleash just unprecedented potential.
That's a powerful way to put it. So thinking about that, imagine the implications for basically any high-stakes, information-dense human job. You know, from emergency response coordination to complex engineering design, maybe even creative problem solving.
Yeah, absolutely.
This isn't just about aviation, is it? It really feels like a new frontier of human-AI collaboration that could genuinely transform how we work, how we learn, maybe even how you think.
It could be that fundamental, yes.
Something for you, our listener, to mull over. We really encourage you to explore these concepts further. Think about how an AI-powered cognitive co-pilot or something like it might impact your own areas of interest or your own work. It's definitely food for thought.